I'm here to talk a little bit about the work I've been conducting, PBT for adversarial reward shaping, and be aware that this is a work in progress. So if you have any recommendation, any suggestion, any idea that you think it would be a nice to explore, please feel free to let me know. I'll be very grateful. Okay. So nowadays we see that autonomous driving systems are becoming a reality. These systems, they are safety critical by nature. They need to be accurately and robustly tested before the deployment. However, how to test them is still an open research challenge. The way that we see in the literature is to manipulate virtual environments such as simulators to cause a perturbation and find a failure, for example, a collision. Then the problem of how to test them becomes an optimization problem that we can apply reinforcement learning to to maximize an objective function, the distance to a misbehavior. And why is reinforcement learning suitable? Because it learns from the interaction with the environment, step by step, dealing and receiving the answer from the environment, and then it can test dynamically the behaviors of an ADS, an adversarial driving systems. When we are talking about solving a problem with reinforcement learning, there are some elements that we need to be aware of. First, reinforcement learning is a learning paradigm with the goal of learning a policy to maximize a reward. We want to map states into actions, okay? So the RL agent will perceive the current state of the environment and will take an action considering that. The action will modify the environment, taking it to the next state. And also, the environment will give the agent a reward, a feedback signal that tells the agent how good the action we take was, considering that specific state. So the reward will guide this agent. It is important because we'll continue with that later. And the objective is to maximize the sum of cumulative reward that it gets in its lifetime. Okay, so when we're talking about testing autonomous driving system, there are some nomenclature that we use. For example, the ego ADS, which is the ADS under test. Okay, it's the one that we want to test. And the way we are testing it is to include an adversarial ADS, another vehicle in the same environment, in the same scene that has the objective of challenging the ego ADS. Considering that through my PhD, my research goal was to use reinforcement learning to train adversarial agents for ADS scenarios using fully autonomous systems and that are able to challenge the ADS on the test and produce learnable failures. We use a case study, one simulator called Highway-Env that supports both single agent, and here we see the ego in green, and one NPC in blue, non-playable character for the people that likes video games. And also it supports multi-agent where we have here the ego and the adversarial replacing the previous NPC. The state space in this environment, you give the state space is how the agent will perceive the environment, and will perceive by having information of the vehicles in the scene, information regarding both position and velocity in the x and y axis. And once it perceives the state, it will take some actions, and the action space is idle, do nothing, go left, go right, go faster, or go slower. We are exploring 3 different driving scenarios. The first one, the highway. The second one, the merge, where the ego has to merge in the highway without colliding with the end of the road. And the third one, the roundabout, where it has to enter and exit the roundabout without a failure. Okay? When we are training the adversarial, we need to design the reward function, because the reward is the piece that will guide the agent through its training. So what we did to reward this design function is we consider 3 different elements. The first one is the quality of driving. We want the agent to drive well, because if it does not drive well, it can collide with NPCs, for example, and will not reach the objective. Then we have this reward that we call distance difference reward, because we want the adversarial to be close with the ego. Otherwise, a collision will not happen. We cannot find this type of failures. And by the end, We have the episodic, the collision reward that is given to the agent at the end of episode. Like here we have episode is split in different steps. In each one of these steps, the agent will take a decision, and then by the end, if there is a collision, it will give this positive reward to motivate the collision, because this is what you want to motivate. So basically, we are rewarding the adversarial when it drives well, when it keeps a closer distance with the eagle, and when it causes a collision with the eagle. Now, this quality of a driving reward is given to us by the environment itself. So we are not touching it, and I'm not talking about it, but I will talk about the other two. And the first one is the reward for the distance differences. And here we have three lines, and I'll explain in a high level what they are doing. The first one, we measure the differences of the velocities, because if the adversarial velocity in our case is in the front of the eagle, so if the adversarial velocity is bigger than the eagle, it means they are getting far away from each other, and a collision will not occur. So we want to penalize this type of behavior. This is the first line. The second one is considering the difference of velocities in the y-axis, because for collision to happen, they must be in the same lane. So if they are not in the same lane, we are penalizing, but not as much as the first case, because it can be a strategy of the agent to change the lane a little bit to later cause the collision. And then in the last one, when this two does not apply, we have a positive reward that is proportional to collision distance. If they are getting closer, we reward positively. Also, we have the episodic reward that, as I said, is given at the end of episode if the collision happened. And basically, for each one of the steps, we have one specific reward. And then by the end, we want to sum this stepwise reward. And the episodic reward will be a percentage of this sum of reward that is collected in one episode. With these approaches, I will skip for this part the quantitative results, but I will show you the types of failures that we were able to find with this reward function. The first one, we see that the adversarial switch lanes in order to cause the collision. In the second one is mimicking the adversarial behavior in order to cause the collision. And the third one, which is my favorite one, we see that they have the distance continues the same, so the adversarial will trick the eagle, so it gets closer, and then the collision happens. This is my favorite. And then we have in the merge scenario, we have the first one when the eagle tries to merge but collides with the adversarial. The second one, the eagle will not even try to merge because the adversarial is too close and will collide with the end of the road. And the last one, it's where he is successful in doing the merge, but we hidden by the adversarial. And then for the roundabout specifically, we have this one where it tries to enter the roundabout but does not succeed. The second one, when we try to exit, but again, collision. And the third one, when it tries to change the lane and hit the adversarial. So these are the types of failures that we found with this reward design. However, design a reward function is very challenging. It's deeply attached with the task being solved and the environment itself, and require domain expertise and a lot of manual experimentation to tune the function and make it work. So in order to try to save some time and effort, our idea is to automate the reward shaping processes by using a technique called population-based training. And what is population-based training? It's an optimization method that has a population of models and hyperparameters and performs both sequential and parallel optimization. So we have, instead of training one model for one entire budget, we will split this budget in small portions. And then we train a population of a model for this small portion of the budget. And at the end, not at the end, at the middle of the process, we analyze the performance of these models. Then it will kill bad solutions, replacing it for some other parameters and continue the training until the end when you have a model that wins the others, let's say like this. Our idea is to apply PBT for reward shaping, where we plan to have a population of rewards And again, instead of training one model with one specific budget, we will use a small portion of the budget specifically. And in the middle, we'll do the comparison based on some selection metrics, such as, for example, the success rate during the training, to see how the performance of the models are going. The idea is to exploit good models, to keep them, and to explore models that are not so good by changing a little bit, by performing mutation, for example, in order to change the parameter and continue. By the end, the model that will control the ADS is the one that won the process at the end. In order to perform the PBT for reward shaping, we need the reward formula, which we already have, and we need to select a delta selection strategies, okay? And what we decided to do so far, we selected these specific parameters because it's the one that will balance the quality of driving and these distance differences, and we selected an interval such as, for example, from 0 to 4. In our previous experiment, we used the value of 0.5 and 2. These values came from us by doing a lot of experimentation. So our idea is to see if we could do better results by using this type of technique. And then we are doing like this. So we first define the first reward with this specific parameter defined, and it will pass through this function that, considering a specific probability, will decide whether to perform mutation or whether to random select a new reward from the range that it came from. Then we keep the first one of the population, and we created the others one that will be trained, that will be used to train the model. Then the reward of this one will again be inputted in this one, and we proceed until the end of the processes. We applied this to our previous environments, and I should say that this is very, very preliminary results. We wanted to see if it was a good direction. Let's see, not formal experimentation yet. But what we saw so far is like we have the highway with 2 configurations using 3 NPCs, 3 other cars, and 5 other cars, and also the roundabout and the merge. And we see that for the roundabout and the merge, we have a population of 3, while for the highway, we have a population of 5 and a population of 8. Here is the test success rate that of our previous experiments. So kind of also gives us a notion of the difficulty of the environment. So we see that the one with 5 NPCs is the most difficult one, for example. So we did a number of repetitions of 5, and repetitions here, I mean that this part is repeated 5 times. So we don't have only one value, but the average of these 5 repetitions, for example. And then the test success rate that we have is like 12 against 18, 27 against 37, 0.3 against 7, and 1 against 3. Which
we see that lower is better.
Yes, thank you, Paul. Yes, sorry, I forgot to. Yeah, thank you. It's better because we want to cause collision. We want to decrease the success rate. Thank you very much. Sorry, I have the context of the experiments in my head. So yeah, this the lowest is the best one. Sorry. Yeah, the lower the best one. But as you can see here, the execution time is something that it's pretty high. I was able to reduce it a little bit, but now it's one of the problems that we need to address, let's say. And I quite understand why it's taking so long, but I didn't figure out how to solve the problem yet. And also, these 2 environments, after did a couple of experimentation of the environment itself, we realized they are quite simple. So you also need to expand what we are doing for other environments or other case studies. So considering that the future work is like we implement a PBT for our case study, and we obtain these preliminary results that obviously need to be careful more depth experimentation. We wanted to expand to a second case study, which in our case means a simulator that has more complexity than the one we are approaching now. And this is the thing that I'm doing now. And then I also want to improve the performance because I wanted to see how the performance of the other goes as well in order to try to have a strategy that deals with both of them. And then to expand to other parameters because now we are using PBT to one only parameters. Maybe it's useful to use for others because we have a couple of them. Then we need to design experimentation, which we started, but we need to see if how it comes. And of course, the last step is to run the experiments. So this is the work I am developing now. Again, as I said, if you have any suggestion, recommendation, questions, please let me know. It will be very helpful. Thank you.